what you have to do is divide the number of possible outcomes in the event, which from now on we'll call the letter E, over, divided by, the number of outcomes in the sample space, which we'll call S. The sample space would be every single possible outcome. So a couple of things that you should realize about probabilities is that the smallest probability there is 0, and the largest probability something has is 1. Something else that you should know is that the probability of something never happening, I'm assuming you know that symbol, something can't happen, is when you'd have a 0. Let me give you...
Why theta? I know it's not theta, but it just looks like theta.
It's called the null set, the empty set, meaning like a circle with a slash through it means there's no things in it, okay? So what I mean is, let's say I said to you, hey, I have one right here. I'm rolling a 6-sided die. What's the probability I'm going to roll a 7?
0.
0. There's no things that are in that sample space. But there's no 7. Okay. Now, if I wanted to figure out if a probability function was valid, if I added up every single probability of every single event in the sample space, the probability altogether should be 1. If I used this as my example, okay, what's the probability of rolling a 1? It's 1/6. I'm going to write here what I'm doing. 6-sided. The probability of rolling a 1 is 1/6, right? What's the probability of rolling a 2? Because how many faces are there? 1/6. Probability of rolling a 3 is 1/6. Okay. If you added that all up, you'd have 6/6, which is 1. This happens to be a probability that has equally likely outcomes. That is not always the case. Okay. I should write some other things down. There's still a multiplication counting principle when it comes to probabilities, okay? So let's say instead of 1 6-sided die, I added 2 6-sided dice. With 1 6-sided die, there are 6 outcomes, right? If I add a second one into the mix, there's 6 ways this could happen times multiplication counting principle. 6 ways, not plus. The other could happen. So when I roll 2 fair dice, there are 6 times 6 or 36 outcomes for that. So just be aware when you are doing multiple probabilities, the multiplication counting principle still applies. Okay? Does that make sense? Let's assume that they're different colors so we can tell the difference of them. Okay? Like this one and that one, 2 separate things. Well, let's find the probability of rolling a sum that's divisible by 3 on a single roll of 2 fair dice. So what we have to do is we have to figure out how many divisible by 3s there are. So let's say on the first one I roll a 1. I'm just going to do some work here. Would you agree on the second one then there could be a 1, 2, 3, 4, 5, or a 6? How many of those are divisible by 3? Let's see, 1 plus 2 is 3, and also 1 plus 5 is 6, which is also divisible by 3, right? So would you agree then, let's just do one more to check, but it looks like with each roll, each first outcome being a fixed number, that's probably going to be the case, isn't it? All right, but let's just check. Let's say I did a 2 first. Then I could have a 1, a 2, a 3, a 4, a 5, or a 6. Isn't there 3 again? The 2 and the 1 and the 2 and the 4. Okay, so that's going to happen 2 times for each of these numbers. That would be 12 out of my total of 36, or 1/3. Okay, how are we doing so far? Can I repeat? Say it louder. Okay, so I just did it with 2 numbers. If I rolled a 1 first, there was 2 outcomes when I rolled a 1 first. There were 2 outcomes when I rolled a 2 first that I got a sum of 6. That's going to continue to happen when I do a 3, a 4, a 5, and a 6. So for every single first roll of one fixed number, there's 2 possible second rolls that give me a sum. So if I had 2 for each of those 6 sides of the first die, 2 times 6 is 12. If you want to write them all out, you can. That's okay too. Okay. Let's talk about, since you haven't ever learned this before, I'm going to have you write some things down over here, okay? So let's say if I have multiple events, if you see the word and, meaning if you wanted to know what's the probability of A and B happening, what you could do is just take the probability of A times the probability of B. This is assuming that there is no overlap in the 2. We'll do a, hopefully, maybe we won't get to it today, but we'll do something if there is an overlap, okay? So, what if it's A or B? This is more when we get to some Venn diagram stuff on the back. Then it's P, the probability of A plus the probability of B minus their overlap. Okay, I'm going to write that and then I'm going to show you what overlap means, okay? In a minute, we're going to get to a Venn diagram where there's, this one says there's 54% of the students are girls and 62% play sports. There's an overlap in girls and playing sports. So some of these 62 are also in this 54. That's what I mean by that. But we'll get to that in a second. Let's deal with something that's just this case up here. Okay? All right. Ooh, Skittles. Always food in here. I don't know why we always do food. Maybe I'm hungry when I do this. All right. 60 Skittles in a bag. These are the distribution of the Skittles. So, common sense here, guys. What do you think is the probability you would reach into the bag and get a green Skittle? 13 green. That's the number of outcomes that I'm counting. So the number of greens over the whole sample space. The whole sample space is the whole bag, which is 60. And by the way, if you weren't given this information, then you just add these up. You can leave it as 13 over 60, or 0.216 repeating. Okay, so I think this is common sense, so I don't think I have to write it down. If I want to do the probability that it's not purple, can't I just figure out the opposite of that and subtract it? So what I mean is, purple is 8 out of 60. So wouldn't not purple be what's left then? 60 minus 8 is 52 out of 60. Stop me if this isn't making sense, because I know this is new for a lot of you. I get 0.86 repeating. Okay, red or yellow. This doesn't say a red and then a yellow. This is one candy. What's the probability it's going to be red or yellow? You add the red and yellows together and you get 21 out of 60. Agreed? Okay. On the next one, I should give you some information about this. And I would have to give you some information about this. There's two things that you would need to know to calculate this probability. Well, one thing really. You would need to know if the candy is replaced or not replaced. Okay, so if the candy is replaced, meaning you pick the green, you put the green back into the bag and then you pick again, then the probability would stay fixed at 13 and 60. Agreed? However, if you don't replace it, isn't the number of outcomes different now? Yes. Okay. So we're going to say if candy, I'm going to show is replaced, the difference, and then if candy is not replaced. Okay. If the candy is replaced, we're going to use this, okay? What's the probability of getting green and green? Well, we're still going to use that. It's just that we have to change our probability. You multiply those together, multiplication counting principle, right? So you would just take the first candy, 13 out of 60, and multiply by the probability that the second is green is 13 out of 60. Is this help making sense to you so far?
So are you saying that would be the case if you took the green one out?
Candy is replaced.
And then you just replace it with a different color?
No. You take it out. With candy it doesn't make sense, but it might make sense with other things. If you took the candy out, you just wanted to see what you're gonna get, put it back in, took a candy out again. Okay. So replaced with the same exact thing.
Okay.
Did you guys get something like that?
Yeah.
Can somebody tell me what would happen if the candy was not replaced? We call this conditional because it's conditioned based on what happened first. So this second probability based on what happened first changes, right? 12 out of 59 because there's no more candy, or one less green candy and one less candy. Wait, what?
We should have done it before that.
Wait, was this on the SAT? No.
Yeah. This time right, I told you that. I said I didn't know how to do that, and that's what I needed help for the SAT.
Just blame me.
Yeah.
It's all my fault.
Now I'm gonna know this. Now I'm gonna know this.
Okay. Do you want me to show you another way you could do this?
Not really. That's a good. No, like because I'm still trying to process this way. I'm overwhelmed. You know what I'm saying?
I'll just tell you that you could use other ways of counting, just like before how we talked about like permutations and combinations can be thought of as multiplication counting principle. Another way you could do this is using combinations. 13C2.
You can show us.
Thanks. If you want to ignore me.
No, I will listen.
13C2, because there's 13 green candies and you're choosing 2. And on the bottom, there's 60, out of all the ways you can choose 2 would be out of 60 C2. Would you confirm for me that you would get 0.044?
Yep.
Okay. Let's talk about, oh. It looks like I'm not going to get to conditional probability, but we'll do that on Monday. We are going to end it with a Venn diagram then. I think, I don't care which example we do. You want to do, this one's harder. We'll do this one. When you're dealing with a Venn diagram, I guess I don't know if you've dealt with a Venn diagram before. Typically, you're given 2 categories to compare. In this case, it's the 54% of the students are girls. I am going to make that one of my circles. Just understand this entire circle then would represent 54% of all the students, the entire circle, okay? I'm not going to put the 54% in there yet. Then we have 62% of the students play sports. That's what we're comparing here. So I'm going to draw another circle and I'm going to make them overlap because these are the percentage of students who play sports. There's one more piece of information that's going to help me. Half of the girls at the school play sports. So what we're going to do is we're going to try to put some different probabilities in here. So I want to know what portion or what percent are girls that are over here, meaning there's no overlap. I want to know what percent are girls who play sports, and this would then be sports, not girls, okay? So, or the boys who play sports, okay? So, 54% represents this whole circle. How can I tell what these 2 are? And did you see what I highlighted in? I didn't mean to highlight in the green. Blue. This part tells me that half of this whole category is right here. So let's split the 54 in half. What does that give me? So 0.27 is over here. That means 0.27 is in here. There's an overlap. Okay.
I messed up now. It's fine.
Are we good?
Yeah.
Okay. Now, if 6.62 is this entire circle, what's this part over here? What is it?
35. Oh,
Is it?
35.
Okay. So I think then, what percentage of the students who play sports are boys? 35% is what we just found. I could ask questions about this too. But this question is, if a student is chosen at random, what's the probability that it is a boy who does not play sports? And on a Venn diagram, you have to realize that sometimes the categories don't cover everything. It's just what I'm comparing at that time. And in fact, this is where we're going to use that all probabilities add up to 1. Okay, so over here we have girls who don't play sports, then girls who do play sports, and then boys that don't play sports, and that adds up to 0.89. What does a probability set have to add up to? 1. So you're right, there's 11% that would be outside this, and if you think about what that category would have to be, that is what's remaining, which would be the percentage of the students that is a boy who does not play sports, or 11%. Okay.